Hello, everyone. So we're going to continue to finish up Chapter 3, normal distribution right now. So we are talking about the theory part of the class. So we're working on distribution. We already finished binomial distribution. That's a discrete distribution. And then now we're working on normal distribution. We already went one lecture about normal distribution. So now we're going to finish it up. Again, the symbols, make sure you're familiar with all the symbols. You should be able to identify them and understand what each symbol means. So sample size, we use the symbol small n, population size, big N, population standard deviation, sigma, sample standard deviation, S, population mean, mu, sample mean, X bar, standard normal variable, Z. So this is Z table, right? Correlation, small r, regression slope, B1, regression intercept, B0, and the probability of observing a sample as extreme or more extreme than the sample collected is p-value. We use p-value to make a decision in hypothesis test by comparing with type 1 error rate, alpha. So we're going to talk more in details when we go to inferences. Okay. So learning objective, we already kind of went through this last meeting for normal distribution. So we need to understand normal distribution is a continuous distribution. So we use a density curve to describe it. The sample space of normal distribution is all real numbers from negative infinity to positive infinity. So normal distribution has two parameters, mu and sigma, population mean and the population standard deviation. So we need to understand how mu and the sigma will affect the look of the density curves. And we should be able to use empirical rule 68, 95, and 99.7% rule to find some specific normal event probability. And the empirical rule used is very limited because you can only find the event probability when it lands exactly on the 7 marks, from -3 standard deviation, -2 standard deviation, -1 standard deviation, and then mu, and then +1 standard deviation, +2 standard deviation, +3 standard deviation away. If the event doesn't land on the 7 marks, then the empirical rule doesn't work anymore. So in general, if you want to find any normal distribution probability, we use Z table, a normal table. So last class, we talked about how to use Z table, right? And once you're able to use Z table to find Z distribution probability, then for any other normal distribution with different population mean and different population standard deviation, all we need to do is do an extra step to convert that distribution into a Z distribution, right? So then we should be able to use normal distribution to solve some practical problems in applications. This is what I already went over last class also. Standard normal distribution, Z distribution, is normal distribution with population mean equal to 0 and the population standard deviation equal to 1. And for any other normal distribution with different population mean and different population standard deviation, it can be always standardized into Z by a simple transformation. Z equal to X minus mu divided by sigma. Right, so we talked about how to use Z table last class. So we're gonna review real quick and before continuing on. So let's work on some practices. So how do we find probability of this event? And then also if we're given the probability for an event, how do we find the cutoff point? Either on a left tail event or on a right tail event, right? So these are what we were referring to last class. So let's look at this. For probability of Z less than 1.444, so you have less than sign, that means it's consistent with the z-table layout, right? So when you look at a z-table, it's less than sign, so it's consistent with the z-table. We can just look it up as is. So the z-score is 1.44. So we'll go to z-table, find 1.44. So 1.4 and 4. Then the corresponding probability will be 0.9251, right? So then the first probability is 0.9451. Right, so verify 1.44, 9251, sorry, 0.9251. All right, that's first event. And the second event, the probability of z less than negative 1.36. Again, look at the sign. It's smaller than sign. It's the same as here, right? So we can look up as is, just like what we did before. And now it's negative 1.36, right? So in the z table, we need to look for negative 1.36. So negative 1.3 and 6. So the corresponding probability will be 0.0869. 0.0869. All right. And next event, probability of z greater than negative 0.67. So greater than sign, we need to change it to be smaller than sign before we go to z table, because z table can only work if you have a smaller than sign, right? So when you change it, it will be 1 minus probability of z less than negative 0.67. So basically, this is to the left of that negative 0.67, and this is to the right of negative 0.67, and total probability equal to 1. So the two areas need to add up to the total distribution. So then we just need to look up this probability now, right? So negative 0.67, we go to the z-table. Negative 0.67, so negative 0.67. The corresponding probability will be 0.2514. So this will be 0.2514. And then you do the math. 1 subtract 0.2514 will be 0.7486. Okay. And next one, probability of z greater than 1.66. So again, this is greater than sign. We need to change it into smaller than by using 1 minus. And then we can look up, right? So once it's smaller than sign, we can look up this event probability with z-score of 1.66. So we're going to look for 1.66. The corresponding probability is 0.9515. So a little calculation, 0.0485. Right? And next one is in between, right? So in between, we need to convert it into the difference of a two less than event. So probability of z less than 1.89 minus probability of z less than 1.55. So if you struggle with this, review the last video, and it's talking about how we find the probability in between. So we have the 3 density curve, right? And this area we equal to this, subtracting this, is very obvious once you draw the density curve out. And once you write it in this way, then they're consistent with the z-table, with the smaller than sign now, right? So you just need to look them up and then do the subtraction. So 1.89, you need to look for 1.89 8, 9. So the corresponding probability is 0.9706. 0.9706. And then for 1.55, we need to look up also. So 1.55, 1.55, the corresponding probability is 0.9394. 0.9394. Okay. Is it? Let's verify 0.9394. Yeah. So then just do the math, right? So 0.0312, right? And next one is very similar to the one we just did. In between, we need to convert it to be the difference of 2 less than. So probability of z smaller than 0.56 minus probability of z smaller than negative 1.23, right? So then we're going to look up 0.56. If we look up 0.56, 0.56. So the corresponding probability is 0.7123. So 0.7123. And then negative 1.23, if we look it up, negative 1.23. So the corresponding matching probability is 0.1093, right? 0.1093. Then we do the math. So 0.6030, right? And the next two are finding probability, are finding z-scores with given probability, right? So this is a reverse lookup. When you given probability and look for a z-score. And here, everything is when you're given z-score, look for probability, right? So don't get confused. For the first one, when you have a smaller sign already, so that's consistent with the z-table, all we need to do is matching a probability on the z-table and find corresponding z-score, right? So we need to find a probability of 0.7673. So all the probability values are inside the table, 0.7673. So we need to look for 0.7673 is right here. So the matching z-score is 0.73, right? So that's pretty easy. So z-score will equal to 0.73. And then the next one, this is just one extra step, basically. I'm gonna make this smaller so it can fit everything in here. So for greater than sign, we know we can't look it up in the z-table because z-table we can only look up when the sign is smaller than. Then for this case, we're gonna just go ahead and convert the sign to be smaller than sign. So there'll be 1 minus probability of z greater than z of 0, right? You can also draw a density curve. So basically, you can think of, you have a normal distribution, and you have a z0 somewhere. Then the probability to the right is probability of z greater than z of 0. And that's given as 0.90. Then to the left of z of 0 will be corresponding to probability of Z is less than Z of 0. And then, you know, the total distribution has to have probability 1. So this probability and this probability has to add up to 1. And that's it, basically. So here we need to use 1 minus 0.9 or equal to 0.10. So basically, you know, the probability to the left of a z-score and the probability to the right of the z-score need to add up to 1, right? That's the total distribution when you add it up. Then the problem become the same as what we did here, except that we have a different probability as 0.10, right? So we're gonna go to Z table, look for 0.10 as a probability. So then when you go to Z table, try to look for 0.10. 0.10 will be on the left-hand side. Everything less than 0.5 will be on the left table for the probability. So 0.10, we have 0.1093, 0.1075, you know, just look around this. And you can see that there is a 1.1003, and that's the closest we can match with 0.10, right? 0.1. Then the corresponding corresponding z-score is negative 1.28. So we can say, you know, we couldn't find exact match of 0.10, but we were able to find the closest as 0.1003, right? Then z of 0 will be negative 1.28. Okay. So this is where we stopped at last class. So this is all different ways of looking up z-table. Either you look up z-table forward from z to p or backward from p back to z, right? So then we know how to deal with, you know, any z distribution problem. Once we know how to deal with z, then for any other normal distribution with different population mean and different population standard deviation, to find a probability or find cutoff point, it's just one extra step based on what we just learned on the z-table, right? So for example, if we have a variable x has a normal distribution with mu equal to 100 and sigma equal to 10, can we find the probability of following event of the normal distribution? Right? Let's go ahead and start. So what's probability of x smaller than 105? So here we need to use the standardization formula, z equal to x minus mu divided by sigma. And then we need to realize mu equal to 100 and sigma equal to 10. That's already given, right? So then for this event, we're gonna do a standardization. So for the event in the middle, for both sides, we're gonna apply the function, subtract the mu, then divide by the standard deviation. So on the left-hand side, it start with x, we subtract the mu, 100, then divide by sigma as 10. On the right-hand side, we start with the number 105, then subtract the mu, then divide by sigma, sigma equal to 10. So the probability will become this, right? And then when you look at this, x minus mu divided by sigma, that's the definition of z, right? So this will become probability of z. And then keep the sign as is. And on the right-hand side is our number. We can calculate it. So 105 minus 100 is 5. 5 divided by 10 is 0.5. So then the x event probability becomes a z event probability. And we know how to look this up, right? So just like this, right? For any z event, you can look up on the z table. So here we have a z-score of 0.5, and the sign is smaller than sign. We can look up as this. So we go to z table, look for 0.50, right? 0.5 is 0.50. The corresponding probability is 0.6915. So this probability is 0.6915. And that's done. And for a second, the same deal. So we want to standardize the event just like what we did on the first one. But the sign here is greater than sign, so just copy the greater than sign as is. So on the left, x minus mu divided by sigma is the same as above, but on the right, the x score is not 105 anymore, it becomes 125, right? So then you calculate. So on the left, x minus mu divided by sigma, that's definition of z. On the right-hand side, we calculate the z-score. So 125 minus 100 is 2.25, and divided by 10 is 2.5. So this becomes a z event as well, right? Then we can look up the probability from the z table. It's just now you have a greater than sign, so you can't look up as is. So please be very careful for the sign when you deal with normal distribution. So we need to use one subtract, right? To convert it to be smaller than sign. Then we can look up of probability of z less than 2.5. So we go to z table again, look for probability of z less than 2.5. It will be 2.50, right? So then the corresponding probability is 0.9938. So 1 minus 0.9938, which is 0.0062. Right, so that's part 2. And then for this one, it's pretty much very similar. So then for in-between probability, do the same process, standardize. Right? It just now you're gonna have 2 signs, right? You have 3 counterparts using the same standardization formula. In the middle is x, right? So the middle become x minus mu divided by sigma. On the left, the boundary is 80 now. On the right, the boundary is 100. Then we go ahead and do the calculation. So the left boundary become 80 minus 100 is negative 20 divided by 10, become negative 2. And keep the sign as is. On the middle, it's x minus mu divided by sigma. That's definition of z. On the right, 100 minus 100 is 0. 0 divided by anything equal to 0, right? So then we just need to continue. Well, this is a z event. Then you should be able to find the probability from z table, just like in this, right? In between, or like this, right? So we need to convert it to be the difference of 2 left tail probability, right? Again, if you're confused about this conversion, please refer to the video on normal distribution part 1, right? So we use density curve to demonstrate why we are able to write it this way. Then we can look up in the z table, right? So now probability of z less than 0. Well, some people may be smart and they say, hey, you know what? I don't need to look up the z table for that. So think about this is a z distribution. Z distribution center is 0, right? Because z is normal 0, 1, right? So population mean equal to 0, and the population standard deviation is 1. If you know the center is 0, that means to the left and to the right, the probability are exactly the same, right? This is the symmetry point. Then probability of z less than 0 will be the same as probability of z greater than 0 as 0.5, right? And if you don't believe me, you can still just go to z table. You know, you look for z score point 0.00, right? So basically 0 is right here, it's 0.5, or you can find a 0 here, right? 0.5, right? The first z score, right? 0.5. Anyway, So that's the first probability. Second probability is z less than -2. So we need to use -2 on the z-score. So -2 is on the left-hand side, so the negative z-scores, -2.00, right? So the corresponding probability is 0.0228. So 0.0228. And the math 0.4772. And that's it. Right. So then for the next two, we need to find a cutoff point for a normal distribution. We know how to find a cutoff point for z distribution, right? We can find z0, but now we need to find x of 0. Okay. So we just need to have one extra step. So when you have probability of x less than x of 0 equal to a given probability, so you can think about you have a normal distribution. This is x, right? So population mean is 100. Population standard deviation is 10. And we're looking for a score somewhere to the, on the x-axis. So this will be x of 0. And you basically need to move the x somewhere on x-axis until you're making the probability to the left will equal to 0.3050. Right? So this is x. We can't look up in the z table with x. We have to convert into z, right? So if we do the standardization, the x distribution will be standardized into a z distribution. So the population mean will become 0. And x of 0 will become z of 0. Right? So all the x point will be standardized into z. But the probability here will stay the same. Right? So when you look for probability of x less than to the left of x of 0 is 0.300, it's equivalent to say you need to find a z of 0 so that probability of z less than z of 0 is 0.3050, right? To the left of z and to the left of x, they have the same probability. And then if that's the case, we should be able to find a z of 0, just like what we did over here, right? With a given probability, we can find z. So then we go to z table, find a z-score matching probability 0.3050, right? But pay attention to the sign. You can only do that when the sign in the event here is smaller than sign, okay? So 0.3050, that's what they need to match. So we go to z table, 0.3050. We have 0.3015, 0.3050 is right here. The corresponding z-score is negative 0.51, right? So we found the z-score as negative 0.51. And now we found a z, but we need to find x, right? So here is the additional step we need to do. We need to convert the z-score into x-score. And how do we convert it? From the formula right here. So here we know what a z is already. Z is negative 0.51. X is the variable we're looking for, x of 0. And the mu is 100. And the sigma is 10, right? So now we just need to solve this equation. Solve for x, right? And if you use x of 0 represent, x of 0 will be equal to 94.9, okay? So I skipped the calculation for solving the equation. If you struggle with solving equations, you can email me and you can join the office hours so we can go over that. But that's algebra skills that you should have learned from the math class, right? Okay. So we understand how to find a probability like this, right? So now the next question is, we need to have a greater than sign. So we want to cut off 10% on the right tail with a greater than sign. Now how do I find x of 0? So make sure you understand this because this is based on the process over here. We just need to do another additional step. So if probability to the right of x of 0 is 0.10, what will be the probability of x to the left of x of 0? Will be 1 minus probability of x greater than x of 0, right? So the total distribution for any distribution is 1, right? So to the left and to the right, they add up to 1. So then this will be 1 minus 0.1 will equal to 0.9. So then the question become something we just did, right? You see now it has exactly the same format, except you have a different probability value. Then we're going to follow the process. Then we need to find the corresponding z0 or equal to. So we need to go to z table. So we need to find the probability of 0.9. Probability are all the 4 decimal place values, right? So don't get confused. 0.9. So the closest we can find is 0.8997 or 0.9015. Again, you can use either one, but as long as you use one of the two neighbors, you're going to be fine. So 1.28. And then from here, we need to solve the equation, right? So we're going to use this equation to solve for x with a given z. Z is 1.28. X is what they're looking for. Mu is 100 and sigma equal to 10, right? So then from here, we can solve x of 0 will equal to, by solving equation 112.8. Okay, so that's all different kind of problem you're gonna encounter for normal distribution, and this is it. There are other practices very similar. If please practice on those. Make sure you're clear about how normal distribution work with a z table. Okay. And the first animal for attendance check, this is a cat. And then now we're going to go to the word problem. So some students struggle with word problem, but basically word problem is just to read some words or sentences and able to apply these theories into here. So there's nothing, different. So basically you just need to, add some reading skills into here. So for example, to be able to compete in their first year of college, the NCAA requires athletes to meet certain academic standard. For students who have 3.0 or higher GPA, their combined SAT score also need to be 800 or higher. Assume the SAT score for students is a random normal variable with mean of 1010 and the standard deviation of 225. So basically from this sentence, we know if we use variable x represent SAT score, x will have normal distribution with parameters mu is 1010, parameter sigma equal to 225, right? And then the question is, what proportion of the college-bound students will qualify for competing in the NCAA game based on the SAT requirement? SAT requirement is 800 or higher, so that means you're looking for probability of x is greater than or equal to 800. If you get these two out, basically that's the same information as what we just practiced here, right? So you have a normal distribution, or here, right? You have a normal distribution with given parameters. You just need to for any event of the not normal distribution, you just need to standardize into Z and define the corresponding probability. And that's what we're doing here. So you have event probability of X greater than 800. Then you're going to standardize into Z by subtracting mu and then divided by sigma. X minus mu divided by sigma equal to Z. So then become a Z event with a greater than sign. And greater than sign can't look up as is, so I need to convert it to be smaller than sign with 1 minus, right? And then you can look it up and a little calculation, you got 0.8238, about 82%, right? Next one, it's very similar. So just the event is different. So earlier we were talking about student athlete to be able to compete in the game. And here is another standard. So students SAT score, if it is below 800, they're not able to compete in the game, but they're still able to receive the scholarship if they are above 620. All right. So the students has SAT score between 620 and 800 will not be able to compete in the game, but they still qualify for the scholarship. So assume the SAT score for the students is random normal variable with mean of 10, 10, and standard deviation 225. Basically, that's just give you the normal distribution with the parameters, right? And the event they're looking for is X in between 620 and 800. And then, just like what we did earlier for this, right? So in between, standardize into a Z in between, right? And then we can look up at the Z table. So it's the same deal here. So you can look up, right? So probability of Z, X between 620 and 800, you subtract mu divided by sigma on both ends. The middle part will become Z. On either end, you can calculate, a Z score. And then in between these scores, you can convert it to be the difference of two left tail probability. And then, just look up and calculate, you have 13%. Right? So here, this is another practice, and this is for look up the cutoff point. So just like what we did over here. So look up a cutoff point, X, okay? So here, the ICT score for students is a random normal variable with mean of 10, 10 and the standard deviation of 225. So basically that gave us the same information as what we talked about earlier. It gave us the normal distribution, right? With parameters provided. And then the question is, how high does a student need to score in order to be placed in the top 10%? Right? So then basically, we need to find a value as a score so that as long as you score higher than that score, you will be placed in the top 10%, right? So when you look at this will be the same as what we just practiced over here, right? You're given a normal distribution and they're looking for a point to cut off the top 10%, right? So once you realize that, then the rest is simple. So with a greater than sign, we can't look up in the Z table, so we want to convert it to be smaller than sign. That'll be 1 minus 0.10 will be 0.9. Then for X event can always be standardized into Z event with the same probability. And then from here, we can look up the Z score with the given probability, 0.9. So I kind of remember it already, 0.9. So the closest we can find is 0.8997, right? So the corresponding Z score is positive 1.28. right? So that'll be 1.28. And then we solve equation, right? So just like the equation here, z equal to x minus mu divided by sigma, right? And then you solve for x, right? So x will be equal to, from here, 1298. Okay, so this is for finding the cutoff point. It's exactly the same as what we did earlier on, the theory part. It just now you need to have some reading, you know, um, and understand the concepts and be able to apply the theories. So this concludes the normal distribution, but we have one more concept to go. Here's a second animal for attendance check. It's a sheep. So this is a practice. One is looking for probability, and the other is looking for cutoff points. It's just like what we did here. So spend some time working on that. And if you have questions, let me know. We can practice that in office hours if you are confused. So the last concept I want to talk about is normal approximation binomial. So now we learn both binomial distribution and normal distribution. They're totally different distributions, right? Binomial distribution is a counting variable. It's a discrete distribution. Normal distribution is a continuous distribution, right? So they're totally different types. But we can still link them together. So sometimes using binomial distribution to find the probability is very, very difficult. So using normal distribution, is a lot easier because normal distribution probability, when you have greater than sign or smaller than sign, you can just standardize and just one step, you can find the probability with just one process, right? For binomial, it's different. Binomial distribution can only find the probability for a specific number, x equal to k, right? And if you have a greater than sign and a smaller than sign, when you have more than one possible outcome in that distribution, you need to calculate one at a time. So it's going to be very, very, very time consuming. So for example, we have a scenario made up here. So we're saying a tire manufacturer, it warranties a defect rate of 10%, which means every tire they produce can have at most 10% of chance of defects. So last month, a delivery of 7,000 tires are produced, and the quality control team randomly selected 200 tires for inspection, and they find out that 25 tires have defects. So then the question is, if we assume the fault rate is 10%, what is the probability to observe 25 or more defective tires? So they inspected 200. So how likely are you able to see 25 tires being defected if you assume the defect rate is 10%? Right? So here, to start, we need to define the variable x as number of defective tires out of the 200 tires. Then this is a count variable, right? Count variable, then it could have a potential to be a binomial variable, right? So we're going to check to see if that's binomial. So there are 4 binomial settings we need to check for. First, do we have fixed number of n observations, right? And we checked. We have 200 tires being checked when you're counting the number of defective tires, right? So fixed n is there. And second, are the n observations independent? Will one tire being defective or not affect the other tire if all the tires are randomly selected? They shouldn't affect each other, so they're independent. And number 3, do every observation have 2 possible outcomes? For every tire, that's every observation, right? After you inspect it, do we have 2 possible outcomes? Yes, right? Either defective or not defective, right? Then between the two outcomes, one outcome is success, the other outcome is failure, right? Which one's success? You need to look at what outcome is being counted, right? You're counting defective tires, that means defective is success. So then lastly, for every observation, does it have same probability of being success? Success is defective, right? And then for every tire, what's the chance of being defective? And we said we assume it's 10%, right? So then after that, you conclude the variable x actually follows a binomial distribution where n equal to 200 and p equal to 0.10, right? Then we're looking for a probability. So probability we're looking for is x is greater than or equal to 25. Then you realize the sample space of the variable will be 0, 1, 2, 3, up to 25, 26, and up to 200, right? From 0 to n. Then from greater than or equal to 25, that means you need to look for probability of 25, 26, 27, 28, 29, 30, 31, 32, up to 200. And for each of them, you use a binomial formula to calculate. You need to calculate like 200 sometimes, right? There's just either easier way to calculate. You can calculate from 0 to 24 also, right? And subtract from 1, but there's still 24 times. That's a lot of the calculation, right? So just like this. For every individual outcome, you need to calculate it using the binomial formula. And this is going to be a hell of a calculation, right? And you can calculate probably it's 0.144894. But the problem is, it's too much work, right? So then here, we're going to introduce a technique so that we don't have to go through that much of trouble by a little bit of approximation, okay? So that's using normal distribution to approximate binomial distribution. Okay, so not all binomial distribution can be approximated. Only if some certain conditions are met, then you are able to approximate. So what are the conditions? We have two. One is for the binomial parameters n and p, we need to have n times p is greater than 10. At the same time, n times 1 minus p need to be greater than 10. If the condition is not met, then don't approximate it. Your approximation will be way off, right? Okay. So then how do we approximate? It's very simple. If the conditions are met and you're ready to approximate, so just instead of saying x is binomial with parameter n and p, we're going to say x is approximately normal with parameter mu and sigma. But where do we get mu and sigma? From the binomial distribution calculation. Mu equal to n times p, sigma equal to the square root of n times p times 1 minus p, right? And then basically you have a normal distribution, and if a normal event, you standardize, you look up on the z table, and that's it. That's a lot easier, right? Okay, so here there's one last thing about the approximation process is, binomial distribution is a discrete distribution, and normal distribution is a continuous distribution. So when you use a continuous distribution to approximate a discrete distribution, you need to correct that continuity continuity correction factor. You need to correct it a little bit so that your approximation is closer. So the continuity correction factor is very simple. For whatever boundaries you have, so for example, we have probability of x greater than or equal to 25, right? We need to adjust this boundary by either add or subtract 0.5 to it. Okay, so how do I adjust it? It depends if you have an equal sign or without equal sign. So if you have equal sign, we're gonna need a either add or subtract. We don't know yet, 0.5. But the purpose is to increase the probability or area. So probability in density curve is just area, right? Okay, so that's the rule. Then if you don't have the equal sign, then we're still gonna either add or subtract 0.5 from the boundary, but now we're gonna decrease the probability. Or area. So common sense, when you have equal sign, you have additional event, right? Your probability should be bigger. That's why we want to increase the probability by adjusting 0.5. And if you don't have an equal sign, then you're missing that point. You have one less outcome, so the probability should decrease. So we try to decrease the probability by either add or subtract 0.5, right? So it's kind of confusing. So let's work on, what we have here. We're looking for probability of x greater than or equal to 25. Then should we add 0.5 or subtract 0.5? So let's look at it. Once you use normal distribution to approximate it, it becomes a normal distribution, right? So then 25 is somewhere. So let's say it's over here. This is 25. So you're looking for probability of x greater than or equal to 25. You're looking for the probability to the right of 25, right? And now you want to either add 0.5 or subtract 0.5 from 25. So it will be either 24.5 or 25.5. So basically you're going to have two options. Either it will become probability of z greater than or equal to 25.5, or probability of not z, it should be x. X is greater than 24.5. But we need to choose the one that's have a bigger probability or area. So which one of these two has a bigger area than this, right? You have an equal sign, you want to increase the area, right? Then it's obvious we need to choose this one because this has a bigger area, right? From 24.5 up to, all the way to the right. So it has additional area right here, right? Okay. So then if you want to approximate using different events, it's all need to go through the same process. And once you do a few of them, then it will become easier, okay? So when you have a greater than or equal to, you're gonna subtract 0.5, but when you have a smaller than or equal to, you're gonna add 0.5 basically. So let's think about it. So if you have probability of x is smaller than or equal to 25, right? Then how are you gonna adjust it? We're gonna draw a density curve. Let's say 25 is here. And less than or equal to 25, it will be from here. all the way to the left, right? So then by the correction factor, it will either become probability of x is smaller than 24.5 or probability of x is smaller than 25.5. But since you have equal sign, you want to make the area bigger. So you need to choose one of the two here, which has a bigger area than this one, right? So which one do you choose? Do you choose 24.5 or 25.5? Since it's less than, you're looking for the area to the left. To increase the area, you need to move the boundary to the right half a point, right? So you should choose 25.5. Okay. So that's continuity correction factor. And then we finished, talking all of those little things. Now we're ready to do the approximation. Okay, so let's work on this now. So we know x is actually a binomial variable with n equal to 200 and p equal to 0.10. To find the probability of x greater than or equal to 25, we now using binomial process, it will be very, very, very hard, right? So we're going to use normal approximation. But first, we need to check, are we able to use normal approximation? So we need to check for conditions. We have two conditions. First is n times p is greater than 10. Is that true? So n times p we can easily calculate, right? That's 200 times 10 times 0.10. That'll be 20, and that's greater than 10, right? So that condition is good. What about n times 1 minus p? Is that greater than 10? N times 1 minus p will equal to 200 times 1 minus 0.10, right? That'll be 180. And that's greater than 10 as well, right? So that, yes, that condition is good. So are we able to approximate using normal distribution? Yes, because both conditions are good, right? So now let's just go ahead and approximate. So from binomial distribution, we can calculate mu and sigma. So mu will equal to n times p. And we just calculated already. That's 20, right? N times p is right here. And now we need to find a sigma. Sigma will equal to, remember the formula, sigma equal to square root of np times 1 minus p. So we're going to copy the formula from here. All right, so we're going to plug in numbers. N is 200. P is 0.10. 1 minus p, 1 minus 0.10. So this is easy to calculate, right? you can use calculator. So I'm going to calculate real quick. That'd be square root of 20 times 0.9. So that's 4.24. Then we can say, x is truly binomial, but x approximately, x follows a normal distribution. And normal distribution has two parameters, mu and sigma, right? Mu and sigma just come from the calculation here. The parameter mu equal to 20, and the parameter sigma equal to 4.24. Now, you're looking for this event, right? Probability. So you can just standardize using the normal event, right? But we need to use the continuity correction factor. So we need to either add or subtract 0.5 from 25 to make it, corrected. And we just talked about this, right? Since they have greater than or equal to sign, this will equal to probability of x is greater than 24.5. We want to make the probability bigger, right? Now we can go back, for the normal process. We're going to standardize this, right? So we're going to standardize the both side of the events. So I'm going to copy the equation from earlier for z equal to x minus mu divided by sigma. It's just the format is bothering me. I just want to have this fraction part. Okay. So it will be a lot easier if you can write on the board. Right, so on both sides, we're going to subtract the mu. Mu is 20. And divided by sigma, sigma is 4.24. Right? And then we're going to do the same thing on the other side. It's just the other side, the score is 24.5. It's coming from here, right? And then subtract mu. Mu is 20 divided by sigma. Sigma is 4.24. Then after standardize, the left-hand side becomes z, and the right-hand side we can calculate, right? 24.5 subtract 20, then divide by 4.24. So it's 1.06. And then this is a z event. We can look up in the z table, but when you have a greater than sign, you need to convert it to be smaller than sign, right? So then we can look up in the z table, which is smaller than sign. A z score is 1.06. So we'll go to the z table, find 1.06. 1.0 is here, 0.06 is here. So the probability to look for is 0.8554. Okay, 0.8554. And then by a simple math here, 0.1446. Okay. So when you compare with the true value from the binomial distribution with so much trouble, is 0.1449. And our approximation is 0.1446. We're only off by 0.0003, right? But how much work did we save? We save a tons of work, right? So that's normal distribution to approximate binomial. Okay. So then this is it. This is concludes the normal distribution here. Normal distribution is the most important distribution in statistics. please make sure you understand the concepts of everything, especially looking at the z tables. That's the most confusing part to a lot of students. So please join my office hours if you have any questions. We're going to stop right here. Thank you.